This video discusses the fundamental theorem of algebra, the Zeroes theorem, and the rational zeros theorem. So far, when solving these types of problems and finding zeros, we've been given a factor or a zero to help us get started. Now, we'll not be given any information to start, so we need to develop a method to search for them. Our first theorem is the fundamental theorem of algebra. This theorem states every polynomial of degree 1 or greater has at least one zero in the complex number system. Well, a polynomial of degree 1 or greater has a variable in it. Degree 0 is just a constant, so degree 1 or greater means that there's going to be a variable. And this polynomial of degree 1 or greater has at least one zero in the complex number system. Really what this theorem says is if you have a polynomial that has a variable in it, there is going to be some sort of zero, a solution when you set it equal to 0 and solve. It might be real, it might be purely imaginary, or it might be complex. This may seem trivial, but this was a huge mathematical discovery. We just take it for granted because we've always been taught that there's going to be an answer, but when this was proven, it was a really significant discovery. Okay, next is our Zeroes theorem. This states for every polynomial of degree 1 or greater, it can be expressed as the product of n linear factors. Hence, the polynomial has exactly n zeros. Note that some of the zeros may repeat. So it's not n unique zeros, just n zeros in general. Oh, we've been kind of using this theorem without knowing it for years. When you solve a linear equation, which is degree 1, you get one solution. When you solve a quadratic equation that's degree 2, you get two solutions. When you solve a cubic, you get 3, and so on. That's what the Zeroes theorem says. You're going to have n zeros. And if we have n zeros, that means we're going to have n factors as well, because for every zero, there is a factor. That's good to know. It just tells us how many answers we can anticipate. The one that's really going to help us get started when solving high-degree polynomial equations and by factoring is the rational zeros theorem. This theorem states if the polynomial function has integer coefficients, then every rational zero of f of x has the form our possible rational zeros will be equal to the factors of the constant term divided by the factors of the leading coefficient. So we're going to find this ratio and simplify the list, and then we'll have our list of possible rational zeros. Please note the word possible. We know that word means not a guarantee. So not every number in the list will be an actual zero of the function, but every rational zero of the polynomial function will actually be on the list. We're going to have to use trial and error to test these possible rational zeros to find the ones that are actual zeros. So let's list the possible rational zeros for p of x equals 6x to the third plus x squared plus 5x minus 2. Our possible rational zeros, it's going to be the ratio of the factors of the constant divided by the factors of the leading coefficient. So let's take a look at our constant. It's -2. We want to list all the factors of -2. What two numbers multiply together to be -2? Well, it could be +1 times -2 or -1 times +2. So our factors are plus or minus 1 and plus or minus 2. We're going to divide these numbers by the factors of our leading coefficient, which is 6. So how do we get a positive 6? Could be 1 times 6 or 2 times 3. But there are actually more options. We could multiply -1 times -6 or -2 times -3 to get a positive 6. So our factors are also going to be either the plus or the minus version. Factors of 6 include plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Now this is certainly not like a list of numbers that's going to be helpful, so we want to simplify this ratio. The first thing I want to talk about when simplifying this are all these plus or minuses. It ends up that a plus or minus divided by a plus or minus is equal to a plus or minus. So let's walk through why that might happen. If I take a positive from the top and a positive from the bottom, a positive divided by a positive is a positive. If I take a positive from the top and a negative from the bottom, a positive divided by a negative is a negative. If I take the negative from the top and the positive from the bottom, a negative divided by a positive gives us a negative. And then our last combination would be if I took the negative from the bottom and the negative from the top, a negative divided by a negative is a positive. So any combination of a plus or minus divided by a plus or minus leaves us with a plus or minus. So every one of my answers is going to be plus or minus. I'm just going to put a plus or minus in the front and then a big parenthesis, and that'll tell us that all of the numbers in the parentheses I should consider either the positive or the negative. All right, now we need to do every possible combination. I recommend you do this in a very systematic way. I'm going to take the first number in the numerator and I'm going to put it over every single number in the denominator. So like 1 over 1 is 1. Then 1 over 2, that's a half. 1 over 3, a third. And 1 over 6 is a sixth. Now that I've taken the first number in the numerator over every number in the denominator, I'm going to move on to the second number in the numerator. So that'll be 2 over 1 is 2. Two over 2 is 1, but notice that 1 is already on our list, so there's no reason to include it a second time. So then we have 2 over 3. That's 2/3, not on the list. And then lastly, 2 over 6. Lastly, 2 over 6. 2 over 6 is 1/3. Notice that 1/3 is already on the list, so there's no need to repeat it. Our possible rational zeros are plus or minus 1, 1/2, 1/3, 1/6, 2, or 2/3. Notice that there are 12 numbers on the list. Our Zeroes theorem tells us there can be no more than 3 zeros for this polynomial. So definitely, not every number on the list is going to work. Now that we know how to find a list of possible rational zeros to help us get started, let's find all the zeros of a polynomial. F of x equals x to the third minus 2x squared minus 11x plus 12. We want to start by listing our possible rational zeros. We know that all the factors are plus or minus. We're going to start with the factors of our constant, 12. So how do we get 12? 1 and 12, 2 and 6, 3 and 4. And that would either be positive or negative of all those numbers. Then we're going to divide that by the factors of our leading coefficient. Again, we know it's going to be all plus or minus. Our leading coefficient is 1. 1 only has one factor. Now we want to do every possible combination to clean up this list. We know that a plus or minus divided by a plus or minus results in a plus or minus. Since the only number we have in the denominator is 1, any number over 1 is that number. So we're just going to have all the numbers from the numerator. 1, 12, 2, 6, 3, and 4. There's 12 numbers in the list. We know that a maximum of 3 are going to work. At this point, we're just going to use trial and error to find which of these numbers are actual zeros. We'll be using synthetic division and then looking at the remainder to determine whether or not they're zeros. Let's start by just picking a number. What sounds good? I'm going to start with 1. I usually always start with 1. And I'm going to synthetically divide it into my f of x. When I do my synthetic division, I get a remainder of 0. So that tells me that 1 is an actual zero of f of x. To get all the zeros, we want to put f of x in factored form. And then we'll set each factor equal to 0 and solve to get the actual zeros. So let's start factoring f of x. Since 1 is a 0, x minus 1 is going to be a factor. And then our second factor comes from the quotient of our synthetic division. X squared minus x minus 12. Well, we could continue to check numbers in our list of possible rational zeros into x squared minus x minus 12, and we could find the additional zeros, but remember that you have other factoring skills. This is a quadratic trinomial with a leading coefficient of 1. All we need to do is find two numbers that multiply together to be a negative 12 and add together to be a negative 1. I think that's a lot easier than continuing to check zeros, so just factor it how you would before you learned this technique. This factors into x minus 4 times x plus 3, and then we'll set each one of our factors equal to 0 and solve to get our zeros. The 0 that comes from x minus 1 is positive 1. From x minus 4, positive 4, and from x plus 3, minus 3. When I first brought up remainder theorem, I told you, I don't use it very often, usually just to check 1. So let me show you now when I use that remainder theorem and how I use it. Remainder theorem says if you plug the 0 into the polynomial and clean it up using order of operations, it'll give you the remainder. Well, when the number you're plugging in is 1, think about what it does to the function. So when I plug in 1, that's going to be 1 to the third minus 2 times 1 squared minus 11 times 1 plus 12. All these 1s, like 1 to the third is still 1, 1 squared is still 1, and then we have the solo 1. 1, when you multiply it by another number, just gives you that other number. So if we add up the coefficients, right, we got like an invisible 1 coefficient here on our leading term. If we just add up the coefficients of our polynomial, that's the same as finding the remainder when you're dividing by x minus 1. When I add these up, I get 0, so I know that 1 is a 0, therefore x minus 1 is a factor. Because it's real easy to just add up the coefficients, that's really the only time I use remainder theorem, but it's a real quick way to check to see if 1 is a 0.